communities and economies by enabling the public to obtain accurate elevation and positioning data. Program priority is to develop models, tools, and guidelines to assess, manipulate, and analyze geodetic data and to investigate the development of a regional subsidence model. I'm sure this will be a very fruitful meeting. Thank you all for participating. Go ahead. Tony will be the first presenter, and I guess, Randy, you'll be the master of ceremonies, right?
I don't hear Randy chiming in. We had a little technical difficulty with some of the government securities. So
can you share screen and show your presentation?
I know how to do that. Yes.
Yeah. So, but I don't know if he gave you the ability to share.
We'll find out.
Yeah.
So anyway, the order of presentations will change just a little bit. I'm going to start off, and then we'll go, and Kathleen can replace me. So let me get Randy to enable the screen sharing for me. It's a lot more fun to present in person because I don't need somebody to point things to me. We're going to get this going in just a second. All right, I presume it's being shared now. And with that in mind, welcome to the C4G outreach of 2021. My topic was particularly about the state plane coordinates and the background for the legislation that will be required to recognize the new state plane coordinates. Why plane coordinates? We're going to start with a little background. Is the world flat or round? So in order to answer that question, let's review it just a little bit, get the concepts. Probably most of us will recognize that instrument on the left, a microscope, but it's a good metaphor for the concepts that we're dealing with ever more precise geodetic positioning. Take, for example, a piece of cloth. Looks nice and smooth with the eye. So a general overview can be modeled very quickly. But if we stick it under a microscope, the more detail we get, the more work it takes to describe what's really going on. Throughout history, as far back as ancient Greeks, they were 8 wind gods. They came horizontally. Each deity had a cardinal direction. The winds were associated with the seasons that they represented. I hope I pronounced them right, but Boreas is the north wind that brings cold air. Notus is the south wind that brings the storms. Zephyrus, west wind from the spring. And Eurus is warning of the coming winter. And there are minor ones for the northeast and southeast, northwest, and southwest. These were important enough to know which direction we were going in, north, south, east, or west. They were personified by symbols. These symbols I'm showing you here are on the Lodinopolis images, which is an observatory, if you wish, that allowed one to find his direction, northeast, southwest, etc. They knew that the Earth was spherical, but placing things on it is a problem, on the sphere. Latitude was pretty straightforward, usually using the pole star, but longitude was always a rough guess without and until we had accurate timekeeping. Now the moons of Jupiter and the ephemeris made it possible to begin getting accurate longitudes, but that didn't work so well for seafarers. Eventually, John Harrison invented a chronometer that began to make it possible to know where you were east-west or with longitude, even while on the sea. However, local surveying is typically still today a matter of plane, distance, and bearing from some starting point. Officially in previous times, it would have been from the town center. Many of the ancient towns had an obelisk in the center of the center of the community, and from which one could describe the property that they had or that they were selling or whatnot. Navigation, however, really was by spherical latitude and longitude, usually by stars and clocks. That's how it's been for a long time, with incremental improvements. But in the 20th century, in the United States, a continental-wide national datum became a reality. The horizontal datum of North American datum of 27 could be treated as a plane coordinates for surveys of very small extent, much like picturing an ant crawling across a beach ball. It seems flat to where he is. And this particular datum fit the area of interest, in this case, the local ellipsoid that fit North America. It wasn't related directly to the center of mass of the Earth. That was pretty difficult to... Excuse me a second, that's not supposed to happen. Amazing leveling campaign, though, resulted in the mean sea level vertical datum of 1929, later correctly renamed to the National Geodetic vertical datum of 29. And in the NAD 27, the Coast and Geodetic Survey developed a system of state plane coordinates for each of the states. It had a design distortion target of better than 1 part in 10,000, which was at the time adequate, and for most cases still is adequate for most boundary surveying. And it served us well for quite some time. But then the middle of the century happened, and in 1957, the Russians launched an artificial satellite called Sputnik. It started something new that created many possibilities for positioning, navigation, and surveying. Satellites necessarily orbit the center of mass of the Earth, enabling the global ellipsoid definitions that now are based on the whole Earth instead of being forced to fit the local areas, even if they're continental in scope. A little bit later in the century, the invention of the electronic distance meter and its common use had an untenable effect of giving surveyors the ability to make observations even more precise than the datum to which they were referencing. NGS responded to that by developing the North American datum of 83, about the same time that the Department of Defense came up with WGS 84. Now, when created, they both were based on the Earth's center of mass within the known precision of the time, which probably was about 5 meters or so. However, WGS 84 was firmly defined to stay based on the center of mass, and 83 was pinned to reference points on the surface of the continent. Now, as I said before, the satellites help define by their orbits where the center of mass was, and our knowledge and the precision of the knowledge of where the center of mass has become positioned with amazing accuracy today. But that left NAD 83 a little over 2 meters away from where we've discovered the true place to be. It's a little like this now. This graph shows you graphically an offset from 2 two identically shaped geoids, but with the origin in two different places. So in 883 and ITRF, in this case 0, which is effectively the same as WGS 84, is actually about 2 meters, 2.2 meters away. It's still within that 5-meter era that they began with. It's just that the N883 wasn't allowed to move while the ITRF was following the best available data, with the result that there can be two sets of coordinates for any point you want to position based on the reference system you're using. Now, well, let me go on. Another thing that is important, and especially to us in Louisiana, is getting heights. The GPS system, and followed by other global navigation systems, has allowed for very precise ellipsoid positioning. In other words, whether it's 83 or ITRF, you can determine relative to that datum, that geoid, I'm sorry, wrong word, to that ellipsoid, you can get from your GPS equipment and system very precise ellipsoid heights as you can the horizontal position. The problem is that is not what determines which way down is. If you define down as the direction that gravity is pulling you here, then the unequal distribution of mass, you have water in the form of oceans on one side, you've got denser materials that are upland, and perhaps other irregularities such as a less dense salt dome, or maybe as you get in the mountains, you've got dense rock or metal deposits, a lead deposit. All of these affect you locally, that so that down is not pointing toward the center of the earth at your place. And the shape of the potential, or think of it as the shape of the strength of gravity where you are, or where everybody is consider that a surface. It's not unlike taking a topographic survey of a lot somewhere, a farmland. You've got the undulations you're showing. You can't see the geoid with your eyes, but if with great measurements, you can determine what those strengths are. And when you do, you can plot that out in such a way that you get what we might call a DTM, digital terrain model of the strength of gravity. It's a little simplified, but it fits the concept. So if you can figure out then how far is the space between that geoid and the more easily measured ellipsoid, you can combine the two so that you can use your GPS to give you an elevation, because elevations are based on the strength of gravity, not on your man-made ellipsoid model. This illustration has an extra component thrown in it called the hybrid geoid. We may be very comfortable with a certain vertical datum in North American vertical datum of 88 is its origin is pinned at a certain benchmark up in Canada and was the best fit for the time that it was created, but it doesn't match precisely the gravimetric characteristics of the Earth. And so in order to get the correct NAVD 88 elevations using a geoid, you have to modify your model from the real, what we'll call the real geoid, the gravimetric geoid, and add that little factor, the red lines you see in there, to create a hybrid geoid. And that's what we've been using. If you've been using your GPS system and getting an elevation out somewhere in the software that you use in the receiver or in your computers later after you download your data is doing that for you. It's taking the ellipsoid height, which the GPS gets, and adding the geoid model to it. I'm going to go on from here. We'll be coming back to that in a little while. But anyway, by the late 2010s, NGS embarked on a new datum for the 21st century. It takes advantage of advances that we've made in both geometric and physical geodesy, and of course, in the advances of computing technology. I'm going to take it by steps for the concept of what's going into our state plane coordinate system and why we even need to bother doing this again. Step one is to come up with Earth-centered, Earth-fixed reference frame. It's basically a Cartesian coordinate system based with the origin at the center mass of the Earth. And the x-coordinate coming out of an arbitrary point, it happens to, for convenience, comes out through the point south of Greenwich, England, where most of the geodetic systems in the world today consider latitude 0. And the y comes out 90 degrees from that, also toward the equator. And the z is perpendicular to both of those and comes in and out of the mean polar position of the rotational axis of the Earth. Step two is something new for this project. They have taken great steps to determine the Euler poles of the different tectonic plates. And you'll see when we get to that slide why that is a great advantage for us, especially for those who want to use coordinate systems. And next, the gravimetric geoid has been improved and is being improved drastically right now by having had some recent years, some satellites that directly measure the gravity potential as they orbit the Earth, and being high up and using the microscope metaphor, it's like looking with your naked eye and you get what they're calling the long wavelength geoid data. They're taking it a next step further using aircraft which fly to much closer to the Earth and getting what might be called the medium wavelength data, using, again with the metaphor, it would be a magnifying glass. And for truth control of or proofing of the data, you can do gravimetric data on the surface of the Earth, which would obviously be way too tedious to go further or to have a great extent, but it helps provide and does a QC on the rest of the data. And step four, this 2021 or 2022 version of the state plane coordinate system is being calculated in such a way as that it's scaled to best fit the topography of the area that the coordinate zone fits or is intended to apply. There will be 4 terrestrial reference frames for your information. The one that most of those in our audience are going to be interested in is NatRev, or the North American Terrestrial Reference Frame 22. Heights will be based on a geopotential datum instead of the hybrid geoid model of NAPGD 2022, and the geoid model is going to be named Geoid 2022. Everyone who's interested in the things we're talking about today should probably grab a copy of these 3 documents about the blueprint for the modernized NSRS. Part 1 is the geometric coordinates and terrestrial reference frames. Part 2 is the geopotential coordinates and datum. And Part 3 is working in the modernized NSRS. If you did get a copy of these, maybe a year or so ago, go back and download them again because they have been updated. Now we're going to review, we're going to get the details of what I was just talking about. Here's a point P that has two sets of coordinates and they're equivalent. One set is the Cartesian coordinates for that x, y, and z axis of x, y, z. And the other one is the latitude, longitude, and height, ellipsoid height. And so those two are equivalent to each other. And depending on which ellipsoid definition you use, you may get different ellipsoid numbers, but GRS 80 and the parameters that are being used today are likely to change if so little in the future as to be irrelevant for most of us who are listening and participating in this program. I mentioned the Euler poles. This slide that was captured from an NGS presentation shows the velocity field of the North American plate. It also, if you look toward the southeast, you'll see something different going on east of Cuba, and you'll see that parts of California seem to be twisting in a different direction. That's all correct. However, if we get coordinates for the Earth-fixed, Earth-centered, Earth-fixed coordinates, they will, they're wonderful. They're the basis for everything we're doing. But if we then use them alone to determine our position, we still haven't accounted, and we'll be showing our coordinates will have a velocity, benchmarks will have a velocity that is represented by this rotation. But in the new system, the Euler pole, which would be the axis of this rotation, is found, and is the velocity, the rotational velocity, is being applied, so that the next result of that is to negate these rotations as far as the local coordinates are concerned. Just as a quick refresher for many, here again, orthometric height is when you combine, it can be discovered by combining both the geoid height and the ellipsoid height. This illustration shows things that are fairly typical, but in South Louisiana in particular, the ellipsoid is typically over the terrain, not under, but the equations all still work. Here's that slide once again. And now, though, the long line that goes from the gravimetric geoid is the one you would use to calculate, would give you the big H instead of the hybrid line that you see at an angle up there. And there's a difference applying the gravimetric geoid versus the hybrid geoid, because there's a slope involved, has this sort of difference, one time, if you will, adjustment that needs to be made to get to the more truthful gravimetric elevations and using the gravimetric geoid. Much less to the southeast and much greater to the northwest. Step 5 is to create state plane coordinates. They're being scaled to the topography instead of the geoid or the ellipsoid. Those of you who've been around long enough to have to do it, you might have measured some distances on the ground and you needed to make coordinates out of them, so you had to scale them down to NAD 27's sea level, or so that because that was the surface that the state plane coordinates were based upon. And so if you're above sea level, Not such a big deal here in Louisiana, but if you were certainly out by the Rocky Mountains or whatnot, very big deal. The scale that goes takes you from what you measured on the ground to what your coordinates would have was significant. NAD83 did something similar, except that in NAD83 it was scaled to the ellipsoid. In fact, back to the 27, it was scaled more or less to the ellipsoid because the ellipsoid was meant to be, the ellipsoid model that they used was meant to fit what they estimated sea level to be across the continent. So in both cases, that was a standard method, except for most, for NAD83 in South Louisiana again, and for a good part of it, the ellipsoid now is above us, and so you'd have to scale up to the ellipsoid. 2022, we should begin to really mitigate any errors that one would make by mistakes in scaling or forgetting to scale or whatnot, because the NGS is graciously calculating new zones for everyone, and one of their criteria is to try to do the scaling of the definition such that it scales well to the mean topography. So in Louisiana, that's pretty good because we're not mountainous. We tend to have, as compared to many other states, we're pretty flat. And the tool that one uses to convert coordinates and do transformations is NCAT, or the NGS Coordinate Conversion and Transformation Tool. All of these things that I've talked about are pretty well explained, and probably a lot more rigorously explained in the 3 documents I cited earlier, and all can be found on NGS website. So what are we coming up with? We're defining a new Louisiana Plane coordinate system. The boundaries will be the same as we have traditionally held. The same parishes will be in the same zones. We've got Louisiana North, Louisiana South, Louisiana Offshore, but we are creating a new, especially with the mapping and the GIS people in mind, a new statewide special zone. For example, this is the preliminary estimation of the results for the Louisiana North. You will see that it has a central parallel. Those who are very observant may notice that it has a central parallel instead of 2 parallels. Because of the method of scaling, there's no difference in having a single or 2 parallels as far as all the math is concerned. But you'll see that by this legend on the right, that the scale factors are pretty good all the way until you get to the very edges of the zone. So you have a distortion value that doesn't exceed 118 parts per million. So it's pretty good for everything except really precise work. In South Louisiana, it's similar. It's a little flatter, and therefore the largest, largest, it looks to me like it's 40 parts per million. The statewide zone is an oblique Mercator projection, called oblique because you might see that the central line is skewed at an azimuth of 53 degrees in some. What this does is allow the extents of the projection and its distortion to be minimized best over the area that we've got concerned. In Louisiana, in this case, has mostly a northwest to southeast arrangement, and this is many times more reduction of distortion than the more often used UTM projection. So I think this should probably be something welcomed by those who have statewide projects or the like. New legislation has several purposes. One is it brings the various statutory entries into one place. Some people call that a housekeeping issue. We have gained some time because of delays in the 2022 rollout. The estimate now is that it will probably be 2024, maybe 2025 before everything's officially out. The NGS, when they started this a few years ago, was asked for representatives from 3 groups in the states with 1 point of contact. And our 3 groups, one was to represent the local, the state surveying societies, and Stan Ards, the past president of LSPS, president at the time of the formation of the committee, Eric Lanier, who is the DOTD Location and Survey Section, representing the Department of Transportation. And the third was to get, if there was one, a geodetic research area in the state, and I represent the state in that regard. And if you need more details, find my email address down there at the bottom. The JCAVEL1 at lsu.edu. And I don't have the comments thing turned on at the moment, but if there are questions and they're worthy of or need an immediate answer, we can deal with that. If not, we can deal with them at the end of the presentation. But let me, on behalf of all the people in the photograph here, our team at C4G, thank you for your participation. And anytime we can be of service, that's what we try to do. Thank you. Do we have any comments, Randy? I don't hear any comments, so hang on a second. I have to stop sharing. How do I do?
Tony, when do you think with the new gravimetry measurements, all these elevations might change?
Well, we live in Louisiana. They're changing all the time, of course. But
with a correction, I wanted to say the corrections from the new gravimetry.
New data. I'm pretty sure that Galen and Dennis are in better position to give you a firm answer. But when the new datum is published, probably in 2024 or so, that's when I think official changes will occur. In the meantime, we're still using the very effective NAVD 88 with the current geoid models, and we can monitor any changes relative to that constantly. I must have changed something because I don't see the place for participants in our Q&A. Wait, here we go. No open questions. All right, well, that's good. Either I bored everybody to death or did it perfectly, and I don't think it's the latter. With that, I don't know if I have the capability of doing so, but Galen Scott of NOAA is up next on our agenda, and I'm going to pause just in case Randy or somebody in the background has control of things, or if not, I will I'll see what I can do. Galen, see if you've got the ability to share your screen or anything.
All right, thanks. Yes, now I do. All right.
I see it. Thank you.
Excellent. Well, great. I'm really glad to be here today. Thank you so much, LSU folks for inviting us. I'm Galen Scott from National Geodetic Survey. I am the Constituent Resources Manager, which means I'm the person that is charged with working with our constituents to try and solicit your feedback on the products and services and tools that NGS is developing, for the modernized National Spatial Reference System. So I'm really pleased to be here today to talk to you about GPS on benchmarks. I want to start off by acknowledging my co-authors here, Dr. Kevin Algren. He's our geodesist and geoid modeler on the GPS on benchmarks team. And Dennis Reardon is our Gulf Coast Regional Geodetic Advisor. He'll be talking to you a little bit later today about data collection methods. And then another person I didn't put on the slide, but is also one of our team members here, is Brian Shaw, who is our GIS guru and now happens to be the Rocky Mountain Regional Geodetic Advisor. So this is a talk, I think this fits pretty well with what Tony went over. Tony, thanks really for setting the stage for me in this talk here. I'm going to go over some of the some similar things and probably talk about it in a slightly different way here. I'm going to give you a brief history of where we're coming from. I'm going to again talk to you more about different types of geoid models, the hybrid geoid models and the gravimetric geoid model. That'll be the foundation for the future. I'm going to talk about the multiple benefits of participating in GPS on benchmarks. We're going to review the data that NGS has and what's still needed, and I'm going to do a live demo of some of the tools that we have for the GPS on benchmarks program. And then I'm going to encourage you all to discuss opportunities to to improve data collection coordination, because we're really, the new paradigm is collecting GPS data and submitting it to NGS so that we can use it in the tools and models that we're building. And we should have time for questions and answers at the end. So a little history here. National Geodetic Survey is part of the nation's first civilian science agency, the Survey of the Coast, which was established in 1807 by Thomas Jefferson after Lewis and Clark came back, and they discussed the importance of accurate maps to support commerce. What started off as a mission to survey the U.S. coastline and create nautical charts for safe navigation and help increase maritime safety. It expanded as the nation grew westward and surveys of the U.S. interior began. So in 1878, the agency was given the new name of the U.S. Coast and Geodetic Survey, which it maintained until 1970. And at that point, the National Geodetic Survey became part of the National Oceanic and Atmospheric Administration. So for much of our history, NGS and our predecessor agencies have collaborated with public and private organizations to establish reference stations at precisely determined locations. As you all are quite aware, right? Traditionally, precise positioning locations were identified by setting a survey mark, right? A permanent mark in the ground. Usually brass or bronze or aluminum discs. And these locations might also be identified by a deeply driven rod or a prominent object like a water tower or a church spire. Over the years, NGS has collected and stored survey data on over 1 million of these survey marks around the country. And then in the 1980s, NGS really helped to usher in the modern era of positioning by finding new civilian uses for the GPS system, right? The Global Positioning System, which the Department of Defense designed to allow them to put a missile through a window anywhere in the world, right? First by using multiple GPS receivers and putting them on known locations, those survey marks. NGS helped to unlock GPS as a surveying tool for the civilian market. Since then, NGS has fostered a series of continuously operating GPS reference stations. These are the cores, as you know. And each of these cores includes a high accuracy receiver that continuously collects the GPS radio signals that are broadcast by the satellites. And in addition, over the past decade, many other countries have launched their own satellite systems, right? And these are collectively known as GNSS, or Global Navigation Satellite System satellites. And these include the US's GPS system, China's Compass system, Russia's GLONASS, and the European Galileo system. Currently NGS relies on, on the GPS signals only, but we are currently building new software that will allow us to take advantage of these other additional systems, which is really going to unleash a lot more power. GPS and the other GNSS systems, as Tony mentioned, and as you all probably know, they provide what we call ellipsoid heights, right? Heights relative to a specific mathematical model of the Earth, which is smooth and of course ellipsoidal. And as strange as it sounds, by themselves, these ellipsoid heights won't tell you necessarily which way water will flow, which is really important for lots of questions and applications. Think sewer pipes and flood maps. For understanding which way water will flow and measuring heights that will tell you which way water will flow, you also need to account for gravity. So by the 1990s, NGS started to develop geoid models or models of gravity for surveyors to use with the ellipsoid heights from GPS. And as we began to add GPS into the surveyor's toolbox and use it with the existing datums of NAD83 and NAVD88, NGS used GPS data on those existing survey control marks to create what are called hybrid geoid models, right? So starting with Geoid 96, NGS has produced a series of 9 hybrid geoid models over the past 23 years, and each one of them incorporating the newest data and the latest advances in modeling. So Geoid 18, which I was the project manager for, and Dr. Kevin Algren, as I mentioned before, was the wizard behind the curtain making Geoid 18. So Geoid 18 is currently the official hybrid geoid model for determining GPS-derived NAVD88 orthometric heights. Now, as we look into the future for the modernized National Spatial Reference System, which we're working on now, NGS is going to provide a purely gravimetric geoid model, unencumbered by warping that nice gravity model to the network of survey marks and giving NAVD88 heights. We're going to be transitioning to the new datum, so the gravimetric geoid, Geoid 2022, will provide the foundation for the promised 2-centimeter GNSS heights in the modernized system. So, going all the way back to Thomas Jefferson and looking into the future, we're really, being able to harness this technology to give us heights at accuracies and in places we haven't been able to get that before. So let me see if I can advance this slide. Oh, there we go. Yes. So speaking of NAVD88, as you all know, it's based on a continental scale geodetic leveling, right? I love this slide, and I see the NAVD88 project manager is out there, Dave Zulkowski. Hi, Dave. Glad to have you on the line. Dave had the honor of hiring me about 18 years ago. So glad to hear you again, Dave. NAVD88 consists of about 800,000 benchmarks connected by about 2.2 million kilometers of leveling, right? I love this idea of these people, these surveyors that literally walked across the country, east to west, north to south, moving their families with them over time, surveying in the north during the summer and moving to the south during the winters. Just the long history of lots of really high accuracy work. The issue with NAVD88, among other things, though, is that it's made of that 2.2 million kilometers of leveling, but that data was collected over about 80 years. And it was the best available data at the time, but it was all matched together. And as we know, particularly down there in Louisiana, the Earth's a dynamic place, right? Things don't stay in the same place. So putting all of that data together that was taken in different time frames definitely introduced some errors into the system, right? So NAVD88 suffers from a known bias of about 50 centimeters and a tilt across the continental U.S. Of about 1 meter relative to the gravimetric geoid, just the gravity model. So you're probably all familiar with this, but I just want to illustrate here how this really affected NAVD88, right? So if we consider here, we have a house with a benchmark. NAVD88 suffers from unknown movements, right? We're not really sure how things are moving in different places from one place to the other. So for an example here, a level line was performed to that benchmark in 1954, right? Between 1954 and 1991, when we released NAVD88, this area sank. It's in an area of subsidence. So in 1991, the original 1954 leveling data was used to compute those NAVD88 heights, and those were published for that benchmark. So that was the published NAVD88 height was from where that benchmark was back in 1954 when it was leveled. However, the true height was much different than that. How much different? Well, we're not sure unless we can remeasure or get an idea of those rates of subsidence. So the true height relative to NAVD88 zero surface is not necessarily the published NAVD88 height because things may have moved in between the time it was leveled and the time it was adjusted. So that was the best technology we had at the time, and it served us very, very well. We've now been able to build, as I mentioned, those geoid models that allow us to use the capability of GPS. And there's a lot of really important survey information that we have collected on those benchmarks that currently serve as the foundation for NAVD88. So GPS on benchmarks is about collecting the data on existing NGS marks that have NAVD88 published orthometric heights so that we can build this bridge between the old system and the new system and to create a transformation tool that will allow you to transform between the old system and the new system. In addition, GPS on benchmarks is really about allowing you and allowing people in the geospatial community to prepare our country and our communities to take full advantage of the benefits of the modernized NSRS. So Geoid 18 is the current hybrid geoid model that will give you GPS-derived NAVD88 heights. A few of the benefits. Right? If you collect GPS data on those leveled benchmarks and you submit them to NGS, we will use that data to improve the local results of the transformation tool that we're going to build to allow you to transform between NAVD88 and NAPGD 2022. In addition, you're also going to get coordinates in the modernized system. And I'm going to talk a little bit more about those shortly here, but 2020.0 reference epoch coordinates will be released with the modernized system, computed from the data that we get. So if you can go out there, collect data on those marks that you use, send that to us, we will adjust that into the reference epoch coordinate adjustment and give you 2020.0 reference epoch coordinates when the modernized system is released. The other important thing here is that by collecting GPS data on these marks consistently over time and submitting that data to NGS, we're helping to provide you with the opportunity to track changes over time using what we're calling survey epoch coordinates. I'm going to go a little bit more into that here shortly. But here's just another couple of examples of what Tony was showing you a little bit earlier here about the relationship between geoids and heights, right? We've got our topography, the surface of the land. We've got a geoid, and we've got the chosen ellipsoid, right? So the ellipsoid height is what we measure with GPS. The geoid height actually comes from the orthometric height comes from leveling, and that's really this big H here between the geoid and the topography. And then the geoid model gives you the difference between the chosen ellipsoid and the geoid. So together, these three types of measurements, the gravity, the geoid model, the GPS ellipsoid height, and the leveled orthometric height, they fit together in this simple equation, which makes evaluating different data sets relatively straightforward. If we have leveled data, we have ellipsoid height data, we can then use that information in this equation to evaluate different geoids and to create a hybrid geoid. So again, the two types of geoid models, the gravimetric geoid model combines terrestrial, airborne, and satellite-based gravity measurements with digital elevation models and math and physics. And Geoid 2022 will define NAPGD 2022 in the modernized NSRS. So the modernized NSRS will be based on a purely gravimetric geoid model. The current prototype for that is the XGeoid 20. For the past 6 or 7 years, each year we've been building and releasing these experimental geoid models that are the prototypes for the gravimetric model of the future modernized system. Over the past 20 plus years, NGS has created hybrid geoid models to convert those NAD83 ellipsoid heights from GPS observations to NAVD88 orthometric heights, right? You know, for the past 20 years, we've been using ellipsoid or geoid models and GPS data to give you NAVD88 orthometric heights, right? That series of models was released between 96 and 2019. We cover all the U.S. states and territories, and to make those hybrid geoid models, we use the GPS on benchmark data to constrain those geoid models to the NAVD88 heights. And again, that current model is Geoid 18, and we created Geoid 18 by comparing, you know, the data that we had across the whole country. So specifically here, the hybrid Geoid 18 and NAVD88 heights, right? We have the benchmarks. These are benchmarks, leveled benchmarks with published NAVD88 heights on the topography. We then used the purely gravimetric geoid model, XGeoid 19. That's the one that we used to create the hybrid model Geoid 18. And then we had the chosen ellipsoid. And so what we did is we collected, you know, we collected GPS data on those benchmarks on the topography, and then Kevin Ahlgren warped that geoid surface to those benchmarks so that when you have GPS data and you apply that geoid model, it gives you the NAVD88 height. Okay, so again, the GPS on benchmark data has been used to take that gravimetric geoid model and warp it into a hybrid geoid model that gives you NAVD88 heights. Right, and again, the equation works the same, and you know that's the idea here of hybrid geoid models, that we create those hybrid geoid models using that GPS on benchmark data. So in the future, well, the issue here, though, is that sometimes this equation didn't close, right? Because for a number of reasons, you know, particularly as I mentioned before, the time difference and the differential movement that happened between the time that the leveling data was collected and the time that the GPS data was collected, right? We're assuming that those were contemporaneous, but in reality they weren't. So it built in some error into the system, and that equation didn't always close. However, for Geoid 2022, it will define NAPGD 2022 heights. Right, so this equation will close every time because it is the definition of NAPGD 2022. So you're going to have, you're going to get your ellipsoid heights. You're going to apply the Geoid 2022 model, and you're going to get your NAPGD 2022 orthometric heights. So we've learned from the past that GPS is a really, really good tool, and we're designing the whole new system with a gravimetric geoid to be able to give you 2-centimeter heights pretty much anywhere. So I mentioned a 2-track approach to new coordinates in the modernized system, right? One of the big benefits of this modernized National Spatial Reference System is time-dependent positioning, and it can account for the fact that the Earth's a dynamic place and things are moving. And sometimes you want to be able to see that motion in the surveys that you're doing, and other times you don't, right? So the reference epoch coordinates are the coordinates that will be estimated by NGS from time-dependent, age-limited historic survey data, along with CORS coordinate functions and an intra-frame velocity model at an official NSRS reference epoch. The idea here is that this is an estimated snapshot of the entire network, and we're going to redo this every 5 or 10 years. So you're going to get 2020.0 RECs when we release the new system. This is a nod to the idea that we want to keep things consistent, and it's really a nod to how we work today, right? Today, we all work in NAD 83 at 2011, epoch 2010. So the reference epoch coordinates will be very similar to that, and they won't change through time. However, people also want to know how those marks are moving, because particularly down there in Louisiana, things are moving at different rates in different places, and we don't necessarily know how they're changing. You're going to hear more about that later when we hear the presentation on synthetic aperture radar that can help to understand how things are moving differently. But survey epoch coordinates are coordinates that are computed by NGS using the data and the metadata that you submit to us, and they're adjusted to distinct epochs through time. The survey epoch coordinates will answer the question, what were the mark's coordinates when it was last surveyed, right? What we're gonna do is we're gonna adjust multiple surveys within time spans that we call adjustment windows. Those adjustment windows for GPS projects are probably gonna be about 4 weeks. So we're going to take a month's worth of data, GPS data that's submitted to NGS from all over the country. We're going to adjust it all together, and we're going to give you a coordinate at the midpoint of that adjustment window. And so if you collect data through time, every month or every few months, you can have multiple survey epoch coordinates that will show you the change over time, how that mark is moving. So you'll have that choice in the new system to use a consistent reference epoch coordinate or the survey epoch coordinates that do incorporate the motion. So GPS on benchmarks has resonated a lot with people across the country, and it's really driven a surge in shared OPUS solutions. So this is a graph of the number of OPUS shared solutions that we've gotten per month since 2007, and you can see from between 2007 and all the way to 2018. They were relatively small, upwards of 250 shared solutions per month. But starting in 2018, we launched a campaign to collect data to improve the hybrid geoid model, to collect data that would go into Geoid 18. And man, folks around the country really responded very well, right? You can see this line here. We broke, record after record every month that year in 2018 with, in terms of new data that was being given to us, being submitted to us. We took that data and we used it. We constrained the gravimetric model to that data to be able to give you an improved hybrid geoid model, Geoid 18. After Geoid 18, we recognized that the next target was collecting that data to create the transformation tool that's going to transform between the old datums and the new datums. So it took us a little while in 2019 to actually make Geoid 18 and get it released. So back in about July of 2019, we relaunched the GPS on benchmarks campaign for the transformation tool. And you could see we slowly got some momentum there through the end of 2019, and then 2020 things started to pick up. We were on pace pretty much with 2018 for the Geoid campaign, but momentum has been really building. And you can see that this year things are going really strong. We're getting data from all over the country. Back in March, we issued a challenge to the community to see if you all could beat the record that was set back in August of 2018 for data submissions, and we did it. You did it, collecting and submitting that data to us. So this is the modernized, the importance of this is that the modernized NSRS will be realized through shared GNSS data. So it's really important for you to start really thinking about collecting that data and submitting it to NGS, because we can use that to build products and tools that you'll need to do your jobs in the future. So I guess Tony showed this earlier, but I'm going to be a little more clear here about this. The relationships between the old datums and the new datums vary by location. And the accuracy of the transformation tool in any particular area is directly related to the density of the GPS on benchmark data that we have in that area to define that relationship between those two systems, right? So when we make the jump from moving from NAVD88 to NAPGD 2022, there's going to be a shift, and that shift is going to be a one-time jump in the 0 to 2 meter range in orthometric heights, right? And that's what this colored map shows, is that shift between NAVD88 and the gravimetric geoid model. GPS on benchmark data is used to measure that shift. You can see it's relatively consistent going, in this direction here, but those colors are slightly different within contained geographic areas. So in order to really define the relationship between these two systems, we need data in all those places to nail it down, right? So GPS on benchmark data is used to measure will be used to measure the shift between the old datum and the new datum, right? You all may have seen this slide before, the shift and the drift, right? I just talked about the shift, and GPS on benchmark data being used to measure that shift. The drift then comes in because coordinates are now time dependent in the new system. The shift will take you to 2020.0. But working in any other epoch means that you need to account for that velocity in your coordinates. And we're going to provide those velocities through what's called the intra-frame velocity model. The name might change in the future, but this is a representative, a model of how the surface moves through time. And you'll hear more about that in the next presentation, hopefully on INSAR. So, that drift, we need that intra-frame velocity model to compute that drift, to move the coordinates through time. Now, we're using right now, this is a prototype of that intra-frame velocity model. We're using a prototype called Trans4D, and we're using that. It's kind of a scoping tool now to evaluate how things are changing, how fast are things changing in different places. And of course, you all know you're in the deep red down here, along with Houston, Galveston area. The idea here is that we really recommend for people in areas of vertical motion of 2 millimeters or more, you really should be collecting and submitting data to NGS to help develop that time series of observations so we can help you track the movement and the changes in those marks over time. So again, Tony mentioned the blueprints, the blueprint documents. In particular, Blueprint 3 is called Working in the Modernized NSRS. The other two give you lots of technical details about how things are going to be built and such, but this one talks about how people will work in the modernized system, the workflows that will that will need to be in place. This was originally released in 2019, but we just redid it in 2020, and this time we included 4 what we call use cases. And this was released back in March, and we have 2 great webinars that are available on our website if you want to go check those out if you didn't see them. March 11th, Dr. Drew Smith talked about Blueprint 3 and all the new decisions and things that we put in there. And then on April 8th, Nick Kinsman led another webinar talking about these use cases. So I encourage you all to get out there, check this out, and check it out. In particular, I'm going to talk about this this one here, this transitioning data to the modernized system, right? Participating in the writing of this Blueprint 3 document really made me and the team reevaluate GPS on benchmarks and the role that GPS on benchmarks plays in this transition to the new system, right? Back in 2019, we had launched the GPS on benchmarks for the transformation tool campaign, right? To gather data to use to create the transformation tool. But then when we wrote this, use case about how you're going to transition data to the modernized system, we came up with this, this order. The best way, these are listed in decreasing levels of accuracy and really decreasing levels of cost. But the best way to get your marks and your projects into the new system will be to get out there and collect new observations and get reference epoch coordinates, right? The second best way is to get, is to readjust your existing projects using, marks and data from that have published reference epoch coordinates. So resurvey or readjust. The third best way is to transform. Lots of people are going to be transforming, but it's not, it's not the most accurate way to get into the new system. There's a lot of people that will need to use, the transformation tools. But what we recognized is that participating in GPS on benchmarks is actually getting out there and resurveying, right? So when you are participating in GPS on benchmarks, you're not just contributing data to the transformation tool, but you're getting out there resurveying these marks, and we will then give you reference epoch coordinates. So, writing this use case here really kind of helped put things into a different perspective for us. So I'm going to pause. I'm going to see if there's any questions, and I'm going to hop out of this and do a live demo of the tools. Are there any questions out there that I can answer? Not hearing any. Okay, I'm not seeing the question and answer panel either, so let's see. All right, so we have released several tools to help you understand where we need data and to make it more efficient so that people can collaborate to collect the data that's needed. This is the GPS on benchmarks for the transformation tool web map application. And Dennis Reardon is going to show you a little bit more later about how to get here and some other things, and I'll show you the link in a bit. But this is the map that shows you the marks that we've identified that we think getting new data on would be most beneficial. So here, if you click, we update this map about every week. If you click this About button here, it'll tell you it was last updated yesterday. So once a week, we take all the new data that we get from GPS submissions to mark recovery submissions, and we update this map. Again, the idea is that we want to have coverage every 10 kilometers across the country in order to create this transformation tool. So we have created, come on now, there we go. So we have created this map that shows you the marks that we need and these 10-kilometer hexagons representing the area on the ground that will be affected by that new data, right? That area will be, with new data, the transformation tool will be better in that hexagon there. So I'm going to go through the marks here. As you know, for surveying, good surveying practice, we need redundant observations, right? We need at least 2 observations that match within a couple of centimeters. So what we do is we tell you on this map whether we need 1 or 2 observations on the mark. Any mark that has a red dot in the center, you can see here, we already have 1 observation. We just need 1 more. Any of these dots that have a yellow center means we need 2 matching observations. Okay. We've also broken them out into priority A and priority B marks, and that's really just based on metadata that we have. The reality is that we will use whatever data that you can get to us, and we just wanted some way to prioritize it. So if you limited resources, go for the A marks first, but the B mark data on the B marks will also be very helpful. So what's important to know here is that these marks that we are listing in this GPS on benchmarks map, they're automatically selected based on the metadata that we have, right? So if I click on this one here, it's going to tell me that it's priority A. We need 2 observations, and it's going to show you. You can get the data sheet from there, right? You can get the data sheet if you want. If you click into that hexagon, though, it'll show you that that's the primary PID that we've automatically selected based on metadata is this one here, represented by that mark. However, any of these other marks, if new data on any of those other marks, will also help and will also, complete that hexagon. So let's say a couple of things. Let's say first thing is that mark's no longer there. It got knocked out in new road construction. Well, you then go down to find one of these marks to collect data on it. If you're doing your recon and want to go and find marks in a particular hexagon, you click on that hexagon and you click this more info button, and it's going to give you all of the data sheets for all of the marks that are shown in that hexagon, right? So not just that primary mark, but it's going to give you the other marks as well. So you can go out there, do your recon, and find a mark that works. The important thing here is that these are automatically selected based on the metadata. What we need is marks with published NAVD 88 heights, right? That's what we need to be able to create the transformation tool. However, if you have a mark that you use that's not in our list, but it does have a published NAVD 88 height, then by all means, observe that mark. We can use that data as well. So that's why I made it clear that we're selecting these marks by the metadata that we have, but you all are the ones out in the field using these marks. So go ahead and observe marks that you need. And if it has a published NAVD 88 height, then we'll be able to use that data for the transformation tool. But even if it doesn't, we'll take that data that you submit to us, and when we do the reference epoch coordinate adjustment, we'll give you the new reference epoch coordinates on that mark that you use when you submit it. So this is a way to not only do the transformation tool, but to prepare your community in the places that you work by collecting the data now so that you'll get the reference epoch coordinates when the new system is released. Let's see. So there's a lot of other good information here. You can do filtering by state. You can do filtering by county. You can look at the attributes of the marks down here. You can export them. There's a lot of great things that you can do with this map to try and understand where we need data and help us help you with new tools. So that's the GPS and benchmarks web map. Are there any questions about that before I move along? Nope. Okay. So as I mentioned, we've set an ambitious goal of 10-kilometer spacing across the whole country. And what we have here is the progress dashboard for the GPS on benchmarks for transformation tool campaign. Again, we're looking for 10-kilometer spacing for the country as a whole. You can see here where that data is. Just like the future, it's not evenly distributed yet across the country. Some places like Minnesota, they've been collecting this data for a long time, and they're way ahead of pretty much everybody. But the idea here is that we're tracking the data that's coming in towards our goals. And what I really like here is to see, down here, this is those 10-kilometer hexagons completed. You can see over the amount of data that was collected. Here's the 2018 Geoid 18 campaign, and then here is the sustained data collection campaign for the transformation tool. You can see it's just been building pretty consistently since the middle of 2019. You can see also that here we're in June of 21, and we are getting close to beating the 2018 high. Last year, of course, was the biggest year of all for this data. But one of the cool things you can do here is we go down here to Louisiana. I'll click on that, and it will update the map. It'll update the map to show the progress in Louisiana, right? So we had a total, there's a total of 447 hexagons in Louisiana, hexagons where we have published NAVD 88 marks. So far, y'all have collected data on 256 of them. So you're over 57% complete for the state, which is great. Y'all, this is going really well here. And you can see here that, through time, folks there were really engaged back in that was 2016. That's the 2016 GPS survey. And then, the amount of data collected over the past couple of years, and by months here. So what's really cool here is you can check not only how you're doing, but you can check against your neighbors. Let's see. So if I click Mississippi, Mississippi's at 17%. Alabama. Alabama's at 9%. So you guys are doing really well. And one of the things I like to do is try and instill a little competition, get people moving on this, because this is one of those things where the more data that we can get, the better we can really serve you and your needs. Moving along to the Opus Shared Solutions dashboard. This is another dashboard that's not focused on the GPS on Benchmarks campaign, but just gives you data for all Opus shared solutions. And this goes all the way back to 2007. And you can see, you can actually switch between down here. These are the dates that the data was loaded, but you can also switch over here to see, by the dates that things were observed, right? So you can see, that Opus Share chugged along for years and years until we really started pushing this GPS on Benchmarks thing, and then we started to see major bumps up in the numbers of solutions. But what I really like about this tool is that it comes over here. You can see who's contributing, right? Nationwide, if we look at it, state agencies are, particularly state departments of transportation, and those with geodetic surveys are by far the biggest contributors across the whole country. Private sector is right up there as well, and the federal government, NOAA and Army Corps and others are down here. Academic institutions and state and local governments are also participating. But if we go in and we look at Louisiana, and I think there we go. It tells an interesting story here. So we look at Louisiana, we can see the Opus shared solutions that have come in from Louisiana. And first of all, what jumped out at me here is that the private sector is far ahead of everybody else in terms of collecting and submitting Opus, collecting GPS data and submitting it to Opus. Federal government and academic community, I guess LSU primarily, are the other contributors here. And the state DOT is not a big user of Opus Share yet. The other thing to look at here, which is really interesting, which is very different than many other states, is that we can look at by mark type, right? The vast majority of marks that have been observed by and have shared Opus solutions are not NGS marks in Louisiana. So if I just look at the NGS marks, right, because for the we need to have the leveling data on those marks to be able to use with that GPS data to make the tools and models that we're building. So what I'm really interested here is observations on NGS marks in particular. So if I go back here, to the agency type. Now it's academic community that is far and away leading with the submission of data on NGS marks, followed by the private sector and the federal government. What I really like about this, and again, kind of stoking a little bit of competition here, you can then zoom in here to this, and let me see if I can make this larger. There we go. There it is, LSU Center for Geoinformatics, the #1 contributor of GPS data on NGS marks in Louisiana, followed by NGS and some private sector firms. And then Army Corps here. So, you know, this is just a tool to keep track of who's submitting what data and where. And I think it's really interesting to see, you know, the partnerships and the collaborations that happen, who's participating in this and who's not, because, you know, the future of the modernized National Spatial Reference System is about using GPS and submitting that data to NGS so that we can continue to update our models and tools. The last thing I'm going to show you here is our mark recovery webpage. We've got this slick new mark recovery webpage, which I really like because it allows you to submit data when you find a mark and let us know whether it's still there. So here's your mark recovery form, and it's got a cool new button called Find Marks Near Me, which I'm not allowed to use because my federal government computer will not give my position away. But it will pull up a map here, and I can draw a new center, and then it will tell me the marks that are around there. And then I can click on one of those marks, and it will populate this recovery form. So the idea here is, you know, that you can collect, you know, go out there, find these marks, and then report back to us whether you found it, whether it's GPSable. You can give us new pictures and such. We also have a cool mark recovery dashboard that I won't go too far into here, but you can see if you do submit a mark recovery, you can then check our mark recovery dashboard to make sure that, you know, that we got it. And I'm going to show you in a minute here. We do have a bit of a backlog of getting these mark recoveries onto the data sheets themselves, but we're doing pretty well with getting them to update the GPS on Benchmarks web map. So if you do, you know, if you go out there, you try to find a mark that's on our list and it's gone and it's been destroyed, you can submit that mark recovery to us, tell us it's gone. Within a week or two, we'll be able to take that off our list and suggest a different one for people to use. So I'm going to go back to my presentation. Let's see. Yep. Okay, there's the mark recovery dashboard. And again, you know, please, if you submit a mark recovery note for marks that you find up to once a year, let us know, did you find it? Is it GPSable? Do you have new photos? Not only does that help us update our maps, but it also helps other people know what marks are out there and usable. We're getting to the end of my talk here. All of this data is out there on the web in ArcGIS format on ArcGIS Online, and people can grab it and make their own tools. So here's the one from Florida, where they have the Florida GPS on Benchmarks web map, and you know, they can provide all kinds of other additional information for people that are using that. What I really like about it is that it allows people to propose observations and let other people know that somebody plans to go out and collect data on a particular mark, so that they can coordinate efforts, so that, you know, you don't have different people collecting data on the same mark when they could be getting data on other marks. Here's the example from Alabama. Alabama just put their GPS on Benchmarks web map together, and they're combining that with some of their DOT priorities of collecting marks on some of the harns there. So this is just another example of a way that you all could help to coordinate, you know, amongst yourselves within Louisiana to make it easier to get the data for your state. So if you've got your own map or a story map or a dashboard or have a great picture or a story about GPS on benchmarks, please drop us a line. This is one of my regular jobs, and we really like to hear from people that are participating. Last two slides, the timeline for getting data to us. We have a small team that's pretty efficient, but there are some things that take longer than others. If you submit a mark recovery to us, we're going to update that GPS on benchmark priority map within about a week. But getting that information onto the NGS data sheet is taking sometimes up to three months or more now, just because we're in a backlog. With the people that we have. Getting data, submitting data through Opus and sharing that data through Opus. Once you confirm that you want to share, meaning that when you share an Opus solution, you'll send in the data, somebody at NGS will look at it, and then they're going to let you know if they approve it, and if they do, you need to respond and confirm that you do want that data to be shared. Once it's shared, it takes about a day after that to get that Opus shared solution to us, and then it'll go into our web map update in about 1 to 2 weeks, and it really depends on what day of the week it gets submitted, because we do those updates. Kevin Algren does the updates to the map starting on Fridays, because it takes over the weekend to do. If you're going to be blue booking data through NGS through Opus projects, those results will get published on NGS data sheets. The time it takes depends on the size and the complexity of the survey, anywhere from 2 to 4 weeks once it's complete. Sometimes, depending on the survey, it takes a little longer to actually to do the blue booking part of it, but from our side, it's about 2 to 4 weeks. And then once it gets blue booked and the data sheets are updated, we'll be able to update the GPS on benchmark priority maps in about 1 to 2 weeks. So there is a bit of a delay. If you submit data and you don't see it appear where you think it should be, outside of these timeframes, please drop us a line and we'll definitely look into it. My last slide here, we're all traversing the path towards NSRS modernization. The cutoff date to get us data for the transformation tool is the end of this year. It's December 31st, 2021. So please try and get us the data, GPS on benchmarks data, before the end of this year. There is a chance that we will be able to use data that's submitted after that, because as you know, things have been a bit delayed in terms of the rollout of the modernized system. So all I can say is that we can guarantee that data that you submit before December 31st, 2021 will be considered for use in the, will be evaluated and considered for use in the transformation tool. Any data after that, I can't guarantee. We certainly want to use the data that you submit, and we will try, but we're not going to be able to guarantee it just because of the complexity of how all the moving pieces in modernizing the system. So we're sticking to that, the cutoff date of December 31st, with some unknown amount of time after that we could potentially accept the data. Get out there, find those marks near you, and submit. Fill out those mark recoveries and send them in. You can stay in the loop by subscribing to the NGS news and the GPS on benchmarks updates. I've been trying to send out regular GPS on benchmarks updates. I've been a little bit behind, but I'm trying to get back to it for June. And you can get ahead of the curve here with online lessons and videos and tutorials. Please check out our website. We've got lots of new great stuff out there to help you help us. And that's it. Folks, the future is already here, but it's just not evenly distributed yet. Please drop us a line. Let us know what you think if you have questions. And also this feedback. We have lots of new products that are coming out. If you check those out, and beta products or other products that you use, let me know what you think. If you have ideas, suggestions, concerns, ngs.feedback@noaa.gov comes to me, and I'll make the connection with the project teams that build those tools. So with that, I will be quiet and see if there are any questions for me.
Galen, this is Tony. Can you hear me?
Yes, sir.
All right, I got 2 questions here. When do you expect engineers and designers to start using the new Datums?
Well, I certainly hope they start using them as soon as they are released. Right now, we don't have an official release date. We did release a delay message earlier this year. And it really, things are kind of in flux right now, right? It really depends on the resources that Congress is able to give us over the next couple of years in terms of when we'll be able to finish the modernized system and release it. However, I will tell you that we have a socioeconomic benefits study that documents the benefits to society and for many different applications that will be derived from using the modernized system. And it's billions of dollars of benefits per year. And there are significant additional early adopter benefits to using the modernized system. So the sooner you can get on the new system, the sooner you're going to be realizing those real dollars and cents benefits that the modernized system will provide.
And a second question, I think you may have it answered on this slide, is a landing pad to access all of those dashboards. Is that the first one, GPS on benchmarks page?
Yes, sir. So the GPS on benchmarks page will get you to that, and that'll get you to the tool and to the dashboard. There's the link for the mark recovery. Geoid 18, I put a link on here in Geoid 18. I didn't talk too much about it, but if you look at the Geoid 18 technical report, there's a section in there about how we did the analysis of the GPS leveling and geoid data to select which marks we use to constrain Geoid 18 in the Gulf Coast. And Dave Zlukowski contributed a lot to that section, and that's in there if you're interested in learning more about the marks that we used within, in southern Louisiana. Oops, sorry.
All right, go ahead and end your sharing your screen, and I will try to introduce Kathleen.
All right.
All right, I got a nod from Randy earlier that we had some technical difficulties, probably having to do with government resources and LSU resources protecting each other from each other. But I believe that Kathleen Jones, she is an expert with the NSAR, works with Jet Propulsion Laboratory in California, and is a partner with us on our current project. Will be speaking by phone, and I believe we will operate her slides for her. And if I have done this correctly, it should be handed off to her and Randy. Hello, Kathleen.
Hello?
Hello.
Can you hear me?
I hear you. Speak up if you can. That's pretty good.
Okay, I'm on my cell phone, so just let me know if I'm loud enough. Yes, Randy and I had a very exciting morning, but we're going to do our best to give you this presentation about this project that I'm doing with LSU and about NSAR in general, because I want you to understand the capabilities and the limitations of the technology. So are we on the first slide?
Indeed.
Okay, can you go to the next one? I'll just say next from now on. And sadly, I put in animation, so you're going to hear next a lot. So as you've probably already seen a slide already showing this, there's a lot of problems with land loss in Louisiana, and it boils down to a combination of subsidence, organic and inorganic sediment deficiency, lack of production of organic soil, and also with changes in the sea level. So right now, the latest measurements show that average subsidence across this area is 9 millimeters per year, which is pretty large, and it's much larger in some areas. And that's driving land loss. And it's also, because it's occurring so rapidly, it's difficult to track what the elevation of these areas are without making frequent updates, which I was only listening to the last presentation, but it sounded like a great discussion of how updates are going to be done now and in the future. Next. So NASA has a large suite of Earth observing instruments, and some of them can be used to address this problem. I show here, all of the missions that are currently on orbit and working in green, and then in orange, the ones that are coming up relatively soon. And I'm going to focus at the end of my talk on the NISAR mission, which is one that is particularly relevant to INSAR observations of the Earth. So just to kind of, next slide, just to kind of give you an introduction to INSAR and what its capabilities are, I go back 5 years ago to something you might have seen in the news about San Francisco's Millennium Tower being observed to sink from space, and it had sunk 16 inches from when over the 7-year period. The title says a photo shows San Francisco's Millennium Tower sinking from space. In fact, it was not a photo. It was a radar image, and it was processed with interferometry with INSAR. It was an image that was taken with the Sentinel-1 spacecraft and instrument, which is operated by the European Space Agency. Next slide. So the data that gave away the hint that there was a problem is shown here. It's a map of deformation versus deformation rate calculated from a time series of images. And that little area that is in the white oval highlights the Millennium Tower. Next. And this is a pretty, what I would call a small signal. I mean, it's consistent and it's across a single building. So there's a lot of reason to believe it. However, after this signal was seen and the European Space Agency provided their results, next slide, please. Tre Altamiro, which is a company based in Italy, got high resolution, very high resolution synthetic aperture radar data, so something like 3 feet, 3 to 9 feet, and used it to process many, many points on the building itself. Now, this kind of capability is really impressive, and so I wanted to show you what could potentially be done with this data. Now, that building is not what the coastal Louisiana looks like. It does not resemble San Francisco. So I'm going to talk about the limitations and what you would have to do in order to use INSAR in the coastal Louisiana area. Next slide. So this is an animation up at the right that kind of goes along with what I'm going to talk about. You collect one image the first time, you measure the amplitude and phase of the backscattered signal. Next click, please. Then you come through again, you collect another image, and you measure the change you measure a new amplitude and phase from the return. And if the surface has changed, like here the surface moved, it actually subsided in a hole, and you see something in the line of sight direction, then that phase change is directly proportional to the change in distance to the ground in the line of sight direction. So for subsidence, you would see a fraction of the vertical change depending upon the line of sight direction that you're looking in from the radar. And that is usually, say, 30 to 45 degrees from a satellite-based instrument. Next slide. So just to kind of highlight what you could do in an area that is not an urban setting, I show you an image collected with a UAV SAR sensor, which is an airborne sensor along the San Andreas Fault in California. Did you go to the next slide? Maybe I didn't say next slide. It says SAR image on it. Can you hear me? Can you hear me? No.
Yes, we're hearing you.
Your
Okay.
voice, your audio, yes.
Okay, and you see the slide that says SAR image San Andreas Fault.
Yes, sir.
So if you click on that, a black square will show up, and I'd like you to keep your eyes on that while I show you what interferometry gives you in that region. So go to the next slide. And now you see an interferogram, which shows a number of different slow creep landslides across that landscape. They are driven partly by the movement along the San Andreas Fault, and of course, exacerbated by rainfall. We get a lot of atmospheric rivers, which dump a lot of rain in that area. So it's extremely useful in some of these bare earth areas and uninhabited areas. Next slide. So synthetic aperture radar comes in many different flavors, and those flavors depend upon the frequency at which they are transmitted. So the wavelength for an X-band radar, you'll hear lots of things about the bands of the radar. The X-band radar has a wavelength that's about 1 inch. And so when you think about scattering from an object with radar, you're going to scatter from an object that's about the scale of the wavelength or half the wavelength. So that really measures the canopy. It does not penetrate heavy vegetation well. It works great on targets that are hard targets and bare earth situations where the ground is undisturbed. C-band has about twice that wavelength. It's about 2 inches, 5.5 centimeters, 6 centimeters. It kind of, penetrates the canopy. You get some canopy scattering. You get some scattering from the branches, and so we call that volume scattering. So it definitely can penetrate sparse vegetation. However, you'll get some attenuation of the signal whenever you have heavy vegetation. And then you go to L-band, which is a 24 centimeter wavelength, so 10 inches. That is really best for measuring below trees and through dense vegetation. Just basically passes through the canopy and it sees the structure of large trees and it penetrates vegetation to scatter from the ground below. Now you will get some contribution, but in general, it's much, much better because of that long wavelength. So next slide. So people sometimes confuse the information you get from INSAR with what you might get from LiDAR. Now, an optical instrument's going to measure color. And over there on the right, did you go to the next slide? On the right, it shows LiDAR, and LiDAR.
The back one, Randy.
Okay, LiDAR, you penetrate through. You'll get a waveform scattered back from both the branches and the top of the canopy and the ground. So you're really measuring surface elevation there, or elevation of the canopy height, or elevation of the branches. But if you have moderate vegetation, you're really measuring surface elevation directly. INSAR, on the other hand, measures change in surface position. So it doesn't measure elevation, and it's along the line of sight direction. And it's usually side looking. So it's a mixture of horizontal and vertical movement if you have both of those at the site. So in this slide, L-band is highlighted with red. So you see it, scattering through to bounce back scatter from the ground. And just to show you a practical implementation within the Louisiana environment, go to the next slide, please. You can see measurements that we made of precursory ground movement before collapse of the Bayou Corn sinkhole. Now, this area is definitely like what we're going to be using NSAR to do. The reason that we got this beautiful signal, which is shown at the top, the NSAR map showing this movement before the cavern collapse, was that we used an L-band radar and we had double bounce scatter from the surface below the trees. So that made this measurement possible. Now, that kidney bean shape is actually a perfect example of the line of sight measurement. The actual deformation was inflow along radial directions into a hole at the center. But because we only measure the component in the line of sight direction, the horizontal movement that was perpendicular to our beam on the ground gave back no signal. So this kidney bean, was actually pattern was a sign of radial inflow at this area. So next slide. Another challenge for NSAR is what we call a loss of temporal coherence. And what it practically means is that NSAR does not work everywhere or all the time. If you look at the example on the left, then what it's trying to show is that the backscatter signal that you get is the sum of all of these returns from everything inside of a resolution cell. And a resolution cell for that TerreStar-X instrument was about 3 feet by 3 feet. For Sentinel-1, it's going to be more like 60 feet by 60 feet. So there's a lot of structure within those things, and you're summing all of those in a phase coherent wave kind of motion way. Now, if you look at the next figure over to the right, what happens is that if the surface is undisturbed, but it moves as a block, then there's no loss of phase coherence. You really get that relationship that I talked about where the phase change relates directly to the amount of movement that occurred in the line of sight direction. Now, as you get changes in the surface roughness, which is the next panel over, then, you get some change in the phase because things changed on the surface over that time. And basically this adds noise to your NSAR measurement of the surface displacement. You're not able to make quite as clean a measurement as you could before. And one way to get around that is to measure a series of images so that the noise, the real signal adds coherently and the noise is added incoherently and reduced by the square root of the number of observations that you make. And then on the final panel is the one that we really worry about, which is when you get total change in the surface. The roughness changes a whole lot, and there, the phase noise is just so great that you can't measure that surface movement anymore. The phase is randomized, and you just can't relate it to what you had before. And a perfect example of this is open water. Open water is perfectly incoherent because it has, first of all, it's relatively flat, and so most of the radiation bounces forward, so you get very little backscatter. And what backscatter you get depends upon the roughness of the surface. And so the wind causes the water to have little ripples on them. Those ripples change on the time scale of seconds. So your surface roughness changes all the time. Now for land, these longer wavelength radars are less impacted by temporal decorrelation because that wavelength is longer, and so phase noise is smaller for a given change in distance on the ground or roughness from that little cell. So the next one, please. So just to summarize the takeaways, for INSAR, you use it for measuring surface displacement and deformation. You can use the fact that it's become incoherent to measure a place where something has changed dramatically. So you could tell, for example, maybe where the vegetation was totally inundated, you would get total decorrelation in that case between the first time you did the imaging and the second time. Second takeaway, only the relative change in surface location is detected, not the surface height. Only the change in the line of sight direction is detected. It doesn't work everywhere. For example, open water, where you have major changes in vegetation or soil moisture. And then last, which is really important for our collaboration with LSU, is that the measurements are relative in both space and time. In time, you're taking two measurements. So you're measuring how much displacement occurred between those two times. So you have to collect a long time series of images in order to reduce the noise, the error bars, and if you have very small changes in the surface. So I would call a few millimeters a year of subsidence a very small change. You will need to take measurements for many years, many scenes, in order to measure that with high accuracy. And secondly, it's relative in space. It's a displacement difference between two scenes points in the image. So if you want to put it in a geodetic frame, you have to tie to a location in the image that has no movement or no movement. And then you can back it out and put it in a geodetic frame. So you need those geodetic control points, GPS, anything. And that's why we are interested in working with the Center for Geoinformatics. So next slide. Just to summarize, the goals and the challenges of this project, as I've kind of motivated, it's going to be very challenging to measure subsidence in Louisiana's wetlands, but also in agricultural areas, because you have surface roughness changes from plowing, you have maybe you have a lot of rainfall. Guess what? Yeah, those kinds of things happen, so it's going to be hard. So what we are trying to do at JPL is to use INSAR and determine where it's going to be able to give good measurements of subsidence in coastal Louisiana. And then second, let C4G know where to focus their geodetic control to expand that utility by giving control points. The other thing is, now after I thought of this, after listening to the last speaker, which is that it also tells you where you need to put instruments in order to measure subsidence, where INSAR is probably not going to be able to work at all. So this is very useful for the work that's being done at LSU. Next slide. There is one little wrinkle. It's a particular challenge for INSAR and wetlands environments, and that's that you can get very high coherence backscatter either from motion of the land, vertical land motion, or from water level change if you have emergent vegetation. On the right-hand side, you see an image that shows backscattering from water to the leaves of and stems of the plant, and then back to the radar. That kind of signal can be very large. You'll get a phase change, but what you're measuring is the water level change. And so we need to both identify areas where you lose coherence, but also areas where you maintain coherence, but it's because you're looking at water level change. So anyway, it's an interesting wrinkle, and I think that it's a challenge also, and I wanted to bring it up. Next slide. So there are a lot of synthetic aperture radar missions in the past and operational now. If you look at this long list, these are past instruments and instruments in operation. You look at the second column, the lifetime, you can see, there's more than 5, 7, 8 instruments that are operational now. But if you go over to the right-hand column and look at access, you can see most of it is commercial, which means you're going to pay for the data. They're probably not going to be acquiring data everywhere unless you paid for it up front. And people who get access to it for free is really limited to scientists who are doing research on things like volcanoes, basic science research, geoscience research. The exception is highlighted there in red, which is the Sentinel-1 instrument, which is free and open. And that is changing the use of INSAR dramatically by making it available to people everywhere, regardless of their ability to pay for the data sets. So next slide. This instrument has a C-band instrument, so it's kind of midway between your optimal L-band and X-band. They have launched 2 identical satellites, which gives them a repeat imaging capability of 6 days. They launched those in 2014 and 2016. The design life was 7 years, so it should last a little longer than that. But they are also committed to continuing with Sentinel-1, C, and D, so they'll launch 2 more satellites. And then when they reach the design lifetime of those 2, they'll launch 2 more. So they want to provide continuity of this data. And in addition, because there's 2 satellites and they've improved, processing capability and things like that, it now images much, I would say more than half of the Earth's surface at 6 or 12-day intervals. It certainly images everywhere on the Earth yearly. But, for what we are doing in Louisiana, you really need that 6 or 12-day interval in order to maintain coherence. So it's got a data set, and if you go to the next slide, they collect data at 12-day intervals on these frames over these areas. And those green dots are the CRIM sites in southern Louisiana. And you can see that they are fully covered by scenes that are regularly collected by Sentinel. So we're processing that data. We've processed all the scenes from 2000 up to 2020, and we've looked at the coherence in order to identify areas where we think we're going to be able to do good measurements. And for starters, we've kind of focused on areas near the CRIM sites because those would be land where the state would have access, and you, in principle, could install geodetic instruments for tie points there. Next slide, please. So this is a map of the coherence that we got from those scenes. This is the mean coherence across the whole time series. It's really a measure of whether INSAR will work. 1 is perfect, so that's the bright areas. You can see New Orleans really well. You see Baton Rouge. You see the cities are very coherent, and you can see, the roads and ways going down into the delta along certain areas. Now, the light gray areas have modest coherence, and so it's not clear whether they will be good or not. Probably the brighter ones in there will have some areas that work, and then the ones that are really dark are very similar to water, and you're just not going to be able to make INSAR work in those areas. So next slide, please. I just set a threshold. I figured out what water looked like. I looked at variability and around both water and low coherence land sites. And if you put that threshold and you say you need a CRIM station within 100 meters of an area where within that 100-meter radius circle around the CRIM site, you have to have greater than 0.35 coherence than the red stations are. And so you can see a lot of the stations just do not maintain enough coherence for you to make a measurement directly at the station. In many cases, you can make good measurements close to the station, and you can see that on the map just by looking at the location of where the CRIM sites are. So the next step that we're going to do is to expand that radius and really try to identify the areas where we are going to be able to make good measurements with INSAR. And let's go to the next slide, please. As part of that, we are contracting with Trey Altamira. Remember, they did the measurement of Millennium Tower, and they will perform INSAR on a subset of this area, an area where it's particularly challenging, but has, like New Orleans, includes New Orleans in it. That's the red outline on the Google Earth map. And we will get measurements of land surface elevation versus time for the locations where the INSAR can be used. And example of that is shown in the maps, the little plots on the right, where you can see a number of measurements during the year showing the change in the surface elevation as a function of time. So that is the end of what I wanted to talk about the project specifically. And now I'm going to talk a little bit about what's on the horizon. NASA is launching their own SAR mission. It's an ambitious Earth observing mission. It's its first mission of this kind to be used for INSAR, for land surface deformation measurements. It's a collaboration between NASA and the Indian Space Research Organization. India is supplying an S-band radar, which is 10 centimeters wavelength, and the US is supplying an L-band radar. So it's like best instrument available for doing INSAR. It was supposed to launch in 2022. It's been delayed to 2023 because of the pandemic. It's got a design life that's like 3 to 5 years, but from experience with NASA instruments, the actual lifetime is usually much longer than the design lifetime. And NASA is already planning on a continuation type mission for this. The repeat orbit will be 12 days, so you'll get a measurement of nearly all of the lands of the Earth's land at that 12-day interval, and you can use that for INSAR. And when I say nearly all of the Earth's land, we're missing the poles, you know, the very, very top of the poles, the land at the top in Antarctica and Arctic. So sea ice in Antarctic, in the Arctic. And we're also not measuring over the Sahara Desert across that long a time frame. The data is going to be free and open to all. And I forgot to put on this slide, but it's really important. There is going to be developed a product that gives land surface elevation change as a function of time that will also be available freely and openly from this data. So in addition to just getting the interferograms, you will be able to find a land surface change maps also. Those are being developed right now at JPL. So just to give you a scale of, let's see, if you look at that picture of the satellite, you see there's kind of this, it looks like a ladder extending down no, that's not a ladder. On the next slide, you can see this 40-foot diameter reflector folded up on the top left-hand side, and that structure holds it in place during launch and before it's deployed. When it's deployed, it's pretty impressive. It's the largest reflector NASA has ever built. It's quite something. And right now, NISAR is being assembled in the high bay at JPL. Both instruments have been delivered, and it's underway. Next slide. So NISAR will have a very wide imaging swath, 150 miles swath, and because you have that very wide swath, you're able to get that 12-day repeat with overlap at the equator, so that you can image all the land surface with that repeat. We acquire data on both ascending and descending orbits. Because the orbits get closer together at the poles, you'll get between 2 and 5 passes over any particular site on Earth every 12 days. Of course, at higher latitudes, you get a lot more passes. So 12 days is sort of the longest time between images that you'll get for any particular site on Earth. Let's see, next slide. This is an animation showing the measurement technique. It's actually very difficult to get a 240 wide swath and measure the backscatter. And so it's got a very complicated method for doing that, where it illuminates the entire swath on transmit, but then on receive, it kind of cycles through the transmit-receive modules, so it samples the return in little tiny segments that correspond to the time when it would be returning from scattering from the Earth's surface. So I'll just keep this animation here, and if you're interested in it, you can look it up online. There's information about SweetSAR. The next slide. So that's the conclusion of my slide. I think we are extremely supportive of C4G's efforts in modernization of the NSRS and are very excited to use NSAR for this. We understand that it's going to be challenging, and so we want to really set up so that when NISAR launches, and even before with Sentinel, we'll be able to use, make it more capable, make NSAR more capable in that area. So this C4G is going to use this to tell where to deploy resources to areas where it can help NSAR be successful. And I just want to close by saying that NASA does a total assessment of all its priorities every 10 years. And in the last assessment of priorities, which is called the Decadal Survey, the measurement of coastal subsidence was given the highest priority. So this is extremely important to NASA too. So I'm done there. I hope that this has been clear, and I'm happy to take questions.
Thank you very much, Kathleen. This is Tony speaking. I have a couple of questions. One I answered from our point of view, but I'm going to pose it to you as well. Are you installing NSAR reflectors in areas where you don't get good coherence? My answer was, it's something we're hoping to study and perfect.
Yeah, JPL is not doing that, and NASA is not doing that. It would be something that one of the agencies would do. Is that your question?
Yeah, I think so. It's something that here at C4G we've talked about for several years.
Yeah.
The second, and in fact, it seems to me that if we find appropriate remote locations that a GNSS antenna matched or attached firmly with a reflector would provide you the temporal change in data that you need.
Yes. Now, we don't even need the reflector unless NSAR would not work in that area. Then you would.
We're assuming the area did not work.
Yeah. Yeah.
All right. And the second question is, oh, I'm sorry. Go ahead.
I was going to say L-band reflectors are very large. They're about 6 foot on a side. So you will have challenges other than just installing them. Like they will subside differently than the ground around them, for example, because of their weight.
Yes.
So you'd have to really work on that.
Some innovation.
Innovation.
The second question is, do you use vertical velocities from cores to validate the INSAR-derived velocities?
Absolutely. Everyone needs that data. That's the only way that we are sure that we've taken out any artifacts from the data. It's absolutely essential that we have that kind of data.
All right. Well, thank you, Kathleen. I don't see any other questions or comments.
Well, Kathleen, I have some questions for
George?
you. This is George Voyages, and I'm interested to know if you can look at the non-floating oil rigs, the ones which are firmly tightened to the floor. Can you get some idea of subsidence for these oil rigs?
Oh, yes. They'll be very bright. Definitely.
Can you provide us that information?
Yeah. If we have the images for that. Yeah.
Okay.
We would have to make a special water mask that didn't mask them out because we apply water masks so that to speed up the processing. That is possible.
Well, the companies that have most of these oil rigs do not allow us to go and put our instruments on the oil rigs, but using INSAR would not be a problem. No one is asking them for permission. We just take the pictures and the echoes and get the information. So that would be great. And the other question is, can you get marine landslides under the sea in the vicinity of our coast?
No, it does. It scatters from the water surface, the very surface.
There's no way. There's no way. Expertise that we can put there to allow us to do that.
Not with INSAR. You might be able to use water penetrating LiDAR for bathymetry. That's possible in some of the shallower coastal areas.
Well, I really would like to follow in the future on this offshore oil rigs, if we can get some, subsidence for those rigs. It doesn't have to be many, just 1 or 2 will be fine. If we can have, a history of those subsidence for the 1 or 2 oil rigs.
Yes. Yes.
Okay, and we have one that we had instrumented it in the past. I think Randy knows about it. Maybe we can be very specific and ask you for that one.
Okay, I can see whether they collected data over it. They don't collect a lot of data over the ocean, but if it's close enough to the shore, then they can collect it. And actually, NISAR plans to collect the entire Gulf of Mexico all the time to facilitate using that data to look for oil spills.
I see. Okay, and what do they collect? I mean, only for the oil rigs, or just see there are patches of oil, floating?
It's we would image the entire Gulf of Mexico. I mean, the water in the Gulf of Mexico on every pass. So a 12-day repeat image of that area, even out in the middle of the Gulf of Mexico.
Thank you, Kathleen.
All right. I don't see any other questions popping up. Thank you, George. That was very informative, and I look forward to some more collaboration between us. To keep things moving, I believe our next presenter is Dennis Reardon, a geodetic advisor for our area. And for most of us, he doesn't need much of an introduction. So I'm going to introduce you to Dennis, and welcome to the club, Dennis.
Okay, thank you. Can you hear me okay?
Yes, hear you well, thank you.
Okay, so I'll go ahead and share my screen here. Hopefully you can see my screen okay.
Looks good, thank you.
Okay, I'm going to turn my video off just as try to save some bandwidth here. So let me go ahead and put it in presentation mode. Okay, so you see just my screen starting slide, I hope.
I see your editing page.
Okay, as far as so you see my first slide with the NGS GPS home benchmark project Louisiana.
Yes, but I see it in the editing mode. Yes.
Editing mode. Okay. What about now? As far as still the same?
Yeah. Try under presentations or down at the bottom right next to the slider on the right. Hit that little yeah, that. That should have worked, but it didn't.
Let me try it through slideshow.
Present online. Or from beginning, all the way on the left.
Still not seeing it correctly?
It must think you have another a second.
Try unsharing that screen and share the other screen.
Let's see. What if I do entire screen? What about now?
I see it now.
Okay. All right. Finally. So, all right. So I wanted to appreciate the opportunity to be a part of what's this outreach meeting this afternoon. And so I just want to kind of, my presentation is really kind of a follow-on to what Galen has talked about. And as far as he talked about the GPS bench on benchmark project overall, and what it's about, what we're trying to do with the information that we get from that. And so I wanted to talk about a little more details on how to participate in that for anyone who hasn't done OpenShare, because basically that is the means of how you submit data and participate in this project. So wanted to show just a little bit about our web page. As far as this was the web page as far as until just maybe a month or so ago. You would get to it through this this web address as far as the ngs.noaa.gov. But we now have a new page. They've updated it, and so there's some things that are You still get to it by the same web address. Some things have, the look has changed and where you access some things, but most of the pull down information that was there before, the pull down menus, those are pretty much the same. We've got a quick access for, they look at, what people access most often. And so they've updated that. There's the Opus, the NGS Explorer, where you can look for, marks via a map. And there's also, other things as far as the coors and the new datums. We also have quick links to other things as far as projects that are going on. As Tony was talking about in the beginning, like the top right of this area has got the State Plane Coordinate Project. And so then there's also options there as far as, updates that we're doing, things that we're, news items that we put out. So, but down at the bottom right, there is the link as far as to be able to get to the GPS on Benchmark web page. And so if you go there, you'll see there's a lot of different options over on the left as far as, there's the recover, observe, report, the web map. It gives you what Galen was talking about, the progress dashboard. And so that there's a link there for that. We also have related links as far as there's NGS, the Data Explorer that I talked about. But there's also a link here as far as for the, Galen talked about doing mark recoveries and the forms for that. There's the option. There's one as far as a actual tutorial video as far as how to do uploads to Opus. So that's something that you could take a look at and access also. There's also we do a couple of different subscriber services, just email subscriber service. And so there's one for the GPS on Benchmark. So if you sign up for that, anytime you get there's a notice that goes out about the program, the project, you will get that and be able to stay up to date on it at all. So that's a web page as far as there. When you look at it, as far as again, like I said, as far as the the participation is basically doing Opus share observations and submitting that and getting those through the overall Opus share process. There's basically 4 different components or parts to that. You do your GPS observations, and those have to be 4+ hours as far as on a published benchmark, or one that had a published orthometric height. There's you do a description, and it's not really looking for a description as like from the the traditional data sheet where it talks about you begin at the post office in the middle of town and you go so many miles out highway, a particular highway. It's not looking for that sort of information, because the solution, the Opus solution data sheet, we call it, as far as it actually has the coordinates on there, and it also utilizes a Google map. And so most anybody can, either use that map or plug those coordinates into their GPS and they can get there. But if the mark is over on the right, it's on the shoulder, and it's covered up with grass, then how do I find it when I get there? How far off a center line? What's the references? Okay, so that's the kind of description that they're kind of looking for on this in an Opus share solution submittal. So you need an accurate antenna height, and you need to know your antenna type, and you need two photos, one a close-up and basically what we call a horizon photo. with these two examples that are on the right. You know, close enough to where you can read the stamping on the disc or the access lid for the mark. The horizon photo kind of gives a view of what's around. You know, better access. You know, it's more information as far as for somebody actually looking to recover it, but also kind of tells people what's around, what obstructions there might be as far as view of the sky if they go to observe or use this mark. So as far as for the GPS on benchmark process, basically, you know, you're going to search the GPS on benchmark web map for marks to observe. You're going to do your field recon to see if the mark is, if it's there, you can use it. You're going to collect your data, and then you will come back, you'll download, you'll submit that information along with metadata that you've collected on that mark. You will be sent once that is, you know, the observations are acceptable, then you will be sent back a draft or a beta version of the solution or how it will be posted onto the web page. And once you approve that everything's correct, then it will be loaded and able to be accessed on our website. And then at some point, as far as after they get that information in and they update, the updates will go to the map, and then you would actually be able to see that as a mark that, as long as it has the number of observations on it, what is being asked for, then you would see that that one is it's finished as far as the number of observations what we need for it. So those are the kind of the 5 processes. I would go into it a little more in detail on those. So Galen had shown you as far as the you know, the how to use and how to access that web map as far as to look for marks to observe. You only want to do ones, like he had mentioned, as far as that had a prior published orthometric height on it. There's this, the priority list is, as Galen mentioned, as far as it really comes from a refined list of what's in the NGS database. In other words, we've gone through and they've run some root algorithms on the database of information to what we have available to try to refine as far as to give a shortened list, a target list, if you will, of marks that we think may be there. I mean, we've had more recent recoveries, you know, and so it's something that hopefully people won't be wasting their time as far as to, there's no guarantee it's there, but hopefully it is, you know. You know, you want to take note of the number of observations, what are needed. Is it need 1? Does it need 2? Whether it's a priority A or B. You know, in other words, A is, you know, that's you want to go for one of those and to start if you can, if it's in a location that's good for you as far as where you want to go and observe. You know, you need to go once, you know, from that you want to schedule your observations as far as and as you know, we talked about there's ways of looking at that as far as is it already gone showing as being complete on our web map, or is it still open as far as needing those observations. You want to read the mark description information for the last, in other words, you know, pick a mark, get the data sheet for that mark, and, you know, look at the description, the recoveries, what's the last recoveries. You know, was it something that, you know, somebody said was, you know, they didn't find it, but, you know, that may be, but if they know, they put a note down there that they looked for the mark, but there was highway construction going on, say for a widening project. Well, then it's very likely that that mark may not be there, So what I did is I pulled a list of marks as far as what's in the NGS database for all the marks what are published. Now this is both, this is showing both horizontal and vertical, and this is not saying that all of those marks are there. That's just what's in the NGS database. So you can use that priority list, but there's a lot of these marks, like Galen had mentioned, as far as that they're probably there. Some of them are being used. It's a favorite mark of some people, but nobody's done a recovery note on it, so we don't know that it's there or not. But if you do, and you certainly, it may not be on the priority list, but if you know it's there, you certainly can observe those marks and to get them updated and to be a part of the project. This is the, just the priority list, as Galen had shown from the web map. And if we zoom in, you can see that there are both A and B marks with the, and some of them, as far as whether they have a yellow dot or a red dot, determine whether they need one observation or two observations. But you can see there's somewhat of a void of information south of 20, kind of north of Alexandria, going out in kind of a V area, triangular area. And some of that, as far as it may be the type of information, as far as it showed on that other map that there are marks in our database that are published through that area. But they may not be ones that we can utilize information from, as far as how their heights were derived. I don't know. I haven't looked into that specifically. Now, the southern part of the state has been historically, or over the last number of years, 20 years at least, area of where is very dynamic as far as vertically, and NGS has been doing updates, control updates through that region, and it's there's issues there as far as because of the way we're publishing, but also marks that that we don't have any information on for the last 30 years, as far as whether those heights are good. We know they're out of date, but we don't know what they are today. So we are suppressing those heights, or we've superseded them. And so there's a database issue as far as, when, it goes to pull that information. And so coming up on the map, there is, I'll talk a little more about that as far as, the marks available and what's coming up on the priority list for the southern part of the state towards the end. So kind of the next step, as far as once you've picked out the marks that you think you want to observe, is you're going to need to go out and recon these marks and make sure that they're there. They're is it in good condition? Is it GPSable? The data sheet might say it's GPSable, but there may have been a lot of trees that have grown up. Somebody put up a building, or who knows what's going on, to where it may not be really accessible for GPS at this time. Take the data sheet, get a copy of that data sheet, print it out, and take it out with you so that you can look at the description, the references, and make any changes, as far as a lot of times, a power pole, a house, different things that were referenced, they may be gone now. So, right on there, the date that you're there, and if you have any new references that you establish, write that information in there, because you're going to need that for doing the mark recovery. You may need it for the description that you're going to submit with OpenShare. You can take your mark pictures as far as you can take that close up and the horizon photos at that time. Check the quality of your pictures before you leave, as far as make sure they're clear and you can read it. There's nothing obstructing the view of being able to see the actual mark in your photo. So again, Galen kind of he talked about it at the very end. This is an example for some of the states through their GIS have taken this GPS on benchmark priority marks list, and they've incorporated that into a state ArcGIS or an Arc web map. And so people, this is the Alabama map, and it shows where you can actually go in there. The purple is where people can actually go in there, select a mark, and schedule that they are going to observe that mark. So this is where it kind of cuts down on that, what Galen was talking about, as far as people observing twice on a mark and wasting efforts in that respect, where you could be observing an additional mark. So once you've gone out, you've reconned it, you've got your, the marks there, it's good, and you're going to observe it. A few things that you need to do as far as before you go out is, one, you need to measure your tripod HI before you go out into the field. In other words, when that tripod is set up and it's plumb, what is it from the tip of that the point to where that antenna reference point is going to sit on the top of the tripod. As far as fixed type tripods, they improve HI measurements as far as the accuracy and consistency of that. But as far as they're recommended, but they're not required as far as for OpenShare submittals. You need to understand, as far as the antenna type and the manufacturers, what they call what is the antenna reference point. There's some of them out there that have a quick disconnect that's incorporated in there, and that adds to the overall HI what you're going to enter in when you submit this information to OpenShare. Again, take your data sheet with you. Make sure on your whoever's doing the observations, they're on the correct mark, but then also take a log sheet with you as far as to fill out, as far as, what is the mark, what's the PID, what's the, start and stop time, what's the date, and what's your HI, what's the equipment that you're using as far as the receiver, the antenna, model and type. And, are there any, what's your overall HI? Are there any issues during the session? So it's good to have all of that information as far as for once you for later. All right. Normally you can. It's a good idea to take additional pictures while you're out there, because sometimes we've seen it as far as where these fixed height tripods, a lot of them have a 1.5 meter, a 1.8, and a 2 meter setting on them. And we've had it to where people, they put it on the 1.8, but it got entered as a 2. And if you have a photo, you can a lot of times you can discern that, whether that was correct or not. There's normally you want to orient your antenna to north. Most manufacturers have, they've engineered these antennas to where they say it really does make a difference, but it does as far as when you start talking geodetic level accuracies. And so they do have a north reference point on there. So that's something that you want to know, and make sure that you put that towards north every time, just adding more consistency to your observation data. During the time of your session, you want to check the tripod bubble, or before you start, check that tripod bubble and make sure it's in adjustment. and it doesn't move as far as throughout the time of your observations. If it's a rod mark, you may need, sometimes these rod marks have a dimple on them, sometimes they don't. So you may need a adapter sleeve to be able to keep that tripod point on the top of that rod mark. It's suggested as far as you put sandbags on the tripod feet and make periodic checks on your equipment throughout your session. This is an example of an adapter. It's a sleeve. It has a place underneath where it fits over a 5/8 inch rod, stainless steel rod, but then it has a hole through the top where it would actually allow the tripod point to sit on top of the rod. This is not an endorsement of the Hickson manufacturing. It is something that's available. We're not endorsing this, but there are other ones out there. This is just one example of it. So that's something that's good to have, really, for any of your surveying that you're doing, where you're incorporating, trying to put a GPS rod, a tripod on a rod mark. So this is where I talk about as far as this is off of the Opus webpage, as far as it shows you some things that are important as far as the measuring that HI, because we're trying to deal with heights. We're trying to get the best heights, the most correct heights, what we can, as far as to determine what's the height of this mark at this point in time. So we want to measure that HI as closely as we can, because we don't want to add any error to our measurements overall and what gets in. There's also antenna calibration, and I'll try to show you this live as far as where you can go to it. But that antenna, that's where knowing your antenna type and model comes into play, because through testing of the field, the antenna phase, the center of that, the electronic center of that antenna, it varies as far as with the height and the path of these satellites, where they are as far as in the overall the sky. And so it changes as that antenna moves. And so we need to, it's all modeled as far as, and so Opus applies that model once you submit your information, depending upon what you enter as far as the antenna type. It cannot automatically read that. So this is why you need to know your antenna type before, certainly before you submit, but you should know it while you're out in the field also. So this is just an example of, this is the traditional NGS log sheet. You want to try to have you guys or yourself, whoever's going out, who's doing the observations, fill it out completely. I mean, you got four plus hours, and so might as well, take that information down while you're there in the field. There is, this just shows an example of where you write on the back of the sheet or on the back of the data sheet. Some of the references, updated references that you'll use to put in when you go to do your actual Opus submittal for Opus Share. There is, off of the Opus, you can get to it from the GPS on Benchmark page or the Opus Share page. There's a modified data sheet or field log sheet. What doesn't require quite as much information as the traditional NGS log sheet. You can print that out and take it with you. Take that with you too. So these are just a couple of photos as far as kind of examples. Like the one on the right, it's blurry. You want to make sure you clear enough off to where you can actually see the mark. If you carry a wire brush with you, just a small one, you can kind of brush it a little bit to where you can read the stamping. This is a good horizon photo. You can actually step back a little more You know, don't have ones where, you know, as far as you can't tell where the mark is. It's good to have something in there, you know, and really don't, you know, we're looking for information about the marks, not really people. So open share, as far as, you know, we talked about it, as far as that there are quality factors that have to be met as far as before we're going to actually accept. And, you know, I do air quotes as far as publish this mark. It's a open sharing, but you can see as far as their, you know, the
Dennis, this is Tony. I think we've lost your sound. This is Tony. I think we've got some technical difficulties with from Dennis. This would be a good time for, while we deal with that, if you have any questions, to bring them forward. I would also, while we're at it, want to express our appreciation of your attendance and participation in today's event. And if I had some bumper music, I could put it on right now. It was very informative, the foundational information that Galen provided earlier on, and really added my supported what I was trying to support with the explanations of why we want to get the new legislation for the state plane coordinates. The other is, of course, Kathleen's presentation was one I was really looking forward to. The use and some of the capabilities of the side aperture radar is intriguing. One of the big challenges, as she noted, is in the vegetated marshy areas, which just happen to be a good part of Louisiana and along the coast. And so the notion of providing the temporal confirmation of geodetic coordinates and the possibility of having some hard reflectors is the sort of thing we certainly are hoping to pursue. And I'm sure with the guidance of her and JPL, we may be successful. I'm going to assign a 5-minute break and see if our technical guys can get Dennis back on the line. And so let's see, what time is it now? I've got 3:50. So at 3:55, somebody will start talking again. So take whatever breaks you need, and we'll be right back. All right, break's almost over. We've got the video and we're waiting to the audio from Dennis. We think we'll be ready within the next minute or two.
Okay, can you hear me?
Sure can.
Okay, so I don't know if I'm still showing my screen. Can you see my screen as far as can you see my screen now?
Yes, Dennis, we can.
Okay.
All right, everybody,
All right, so
come on back. Our break's over, and I think Dennis is ready to continue his presentation. Go ahead, Dennis.
okay. So I think you had lost, you know, as far as I was told that you lost it a couple slides back. So I'll just go back to this one as far as talking about the quality factors. So there are a couple of you know, quality control factors what need to be met as far as for a solution to be shared on the NGS webpage. So, you know, one of the easier things to do as far as you want to make sure before you go through the process of putting all your metadata and your photos and all of that, and just check your observation file, and you can do that by just submitting it to the normal Opus. Do not share it. Just send it to Opus, and it'll send you back a solution, and you can check these values as far as the you know, make sure that greater than 70% of the observations and the ambiguities are observations used and ambiguities fixed. Your overall RMS is less than 3 centimeters, less than 4 centimeters on the peak to peak for the latitude and longitude, and then less than 8 on the ellipsoid height. So once you know that, then you can go ahead with the rest of the information what you're going to need to actually submit to Opus. So you know your information, your observation file is good. You've got all your metadata. You're going to download your observation file. You've already done this actually if we've submitted to Opus, but you may or may not have to convert to Rhinex because UNAVCO has said that they are no longer supporting TEQC for the higher versions of Rhinex and making all the converters as far as for, you know, the particular manufacturers out there. So you may have to take their the whatever brand equipment you've got, take their converter and convert your file to a Rhinex for submitting. Again, you need to know when you go to submit, you need to know your particular antenna model and type and the version. You want to edit your to-reach information. So write that information up in like in a text editor or Word, some sort of processor. So that you can take that, you've already done your spelling, whatever you want to do, you can just copy and paste it in. You don't have to type it in online. If any edits that you want to do to the pictures, we do have a program. It's called free. You can download. It's called DS World. That'll allow you to go in there. You can shrink the size of the photo, but without sacrificing quality. So it allows you to do that. You can put, you can put, enter the PID of it. It'll rename the photos. So if you want to do those sorts of edits, you don't have to for submitting to OpenShare. You do want to wait a number of hours. So, you know, don't go immediately once you get back. You need the time for the ephemeris files to be developed and available for processing your data. So, you know, you do it in the afternoon, you come in the next morning, submit it the next morning. Okay. So again, as I mentioned, as far as submitted to Opus, just a regular Opus first to check your quality factors. Once you know everything's good, then you're ready to submit. But so you would go to the NGS webpage as far as for Opus. and there's a number of pieces of information here. I think I was going to try to do it live here. So let me just go to our web page here. So if I go to the Opus page, so this is where you would submit your information. And just for people's knowledge, as far as there's all of the red text is actually a hot link to more information. So it will if you want to know as far as, well, what are they asking for as far as antenna height, it will take you to another page that has lots of information about Opus, and it will give you that diagram that what we talked about as far as for what it's looking for as far as the HI. If you like on the antenna, it will actually, it goes back to that same page. You can get to it off the NGS web main page, but there's also a hot link right here. Hopefully you can see my pointer where it says antenna calibration. So that will take you to the NGS antenna calibration page, where you can go down and let's just, we'll just use the Trimble, for example. So you go to Trimble and there's a couple of different, categories. There's one that tells you the code, or it has a column for the code, random code, images, who the calibration and what kind of calibration it was by, type that was done, the description of the antenna, when that calibration was done. It tells you as far as for the antenna reference point, it's and you can get there's a list as far as all these acronyms. So if you click on that, it'll go to it. But like this one is the bottom of the antenna mount. The north reference point is the TMT. Well, what is that TMT? So if we go down here, we can see that is the tape measure tab as far as off of the antenna. So apparently it has a little tab where you can use a tape measure to measure down to the mark, get your HI, and that is the north reference point. So there's lots of information that you can get there. But as far as, let's just say that you were using a 41-249 antenna, well, there's several different ones here. There's a SCIT, there's a none, there's a TZGD, and there's another one that's a USCG. And so you want to know which one is the correct one for matching to your information. So one, you can look at it as far as the drawing of the antenna. You can see where it has the label. It has a side view, and you can see it's just the antenna versus this SCIT, where it actually shows, well, it's not that one, it's this TZGD. If you look at the side, it actually has a radome, which does change the antenna phase center. So you want to make sure that whenever you go to do your selection for submitting your data, you pick the TRM 41-249 none. So you want to make sure you get that one, because most likely you do not have a radome that you're collecting your information. So that's the antenna ref as far as calibration. So you want to make sure you have all that information, that before you go to actually submit to Opus. So you're going to put in your antenna height, put your email in, and then before you go and hit upload to static, you want to tell it, yes, I want to share my solution. If you don't select that, it's just going to go to regular Opus. So, and it will not share it. You'll just get a solution report back, and that'll be the end of that. So, so I've talked about the antenna calibration. So let me go back. So as far as once you've got all that information, you've entered, and from that open submittal, once you say yes, I want to share, and you hit the upload to static, then it will go to the next page, and it'll ask you for what's the PID, give me your descriptive information, connect me to the photos that we're going to upload for this. So it'll ask you all that information once you say, yes, I want to share. So let's say that, we're to the point, you've done all that. Once that has been received and reviewed as far as by people at the headquarters, then they'll send you basically a draft version of the mark and what it will look like. And you just need to look over the information as far as, is it showing the right mark? Does it have the correct photos? Is it in the right location? Is there, as far as all of that is just the to-reach description information, is all of that correct? And then so once you've looked that over and you send back an email saying, yes, all the information is correct, then within a short period of time, that will get uploaded and it will be available on the OpenShare webpage. Galen had talked about as far as the various times it takes for things to happen. But once, your observation gets accepted and uploaded to OpenShare, well, then within a certain period of time, it's going to show up on that GPS on benchmark web map as being complete once it, however many observations it was asking for are there. So this is an example of, what the solution looks like, or what the Opus data sheet looks like. This is what you'll review before it goes up, and then actually what would be there afterwards too. So, and that just shows you a little closer what it looks like as far as the marks, where it shows, the ones that are complete, as far as we've got the number of observations that were being asked for. So, something else I want to talk about and kind of take the opportunity. I've just got a few more slides here, but I want to talk about as far as this is kind of in reference to the southern Louisiana. So we've done 4 different surveys to update control in southern Louisiana, and so the last one was the 2016 survey, and we very similar to the 2010 survey. That one got caught up in the first multi-year core solution, which created a need for the NAD 83 2011 national adjustment, Geoid 12B, or Geoid 12, which turned into A and then B. But so anyway, so the 2010 survey actually got caught up in all of that and didn't get published until, I'd have to look back, but it was somewhere after it was either very late 2012 or early 2013. So similar to that, this 2016 survey has gotten caught up in several things as far as there was another multi-year core solution, Geoid 18. The 2016 survey, the information from that was a part of the Geoid 18, but it's also got caught up in a number of these projects that are going on as far as the NSRS modernization. And just like, having creating a delay of us publishing that, the modernized NSRS, this 2016 survey is the same things happened to it. So, it was a project entirely, carried out as far as initiated and carried out by NGS. It was NGS crews that did the observations. We did there were about 160 marks overall, actually, somewhere in that range. We did accept and work with some volunteers as far as they wanted to do observations. Calcasieu Parish did a number of observations and got that data to us to be included. Also the Corps of Engineers, and then the Nickel State, they submitted information. So those were added into it. Another thing that kind of took longer for this survey, this project, was prior to this, as far as for the 2004, 6, and 2010 surveys, excuse me, when it came to the, they're all processed relative to the cores, so the processing was not an issue. It was when it came down to the overall network adjustment. And so the first 3 surveys we utilized, and the vertical adjustment is really the harder one. Okay, the geometric adjustment, basically the horizontal that produces the latitude, longitude, and ellipsoid height, that one's easy. I mean, as far as we get that we tie it into the cores, we constrain them, and we get a good and consistent result from that. When it comes to the vertical adjustment, that's because we're trying to tie this to NAVD 88, and knowing what heights are most probably correct as far as to constrain that network, the vertical component of that network, to tie it to NAVD 88. That's the hard part coming up. The first 3 surveys basically used what was called the vertically time-dependent positioning model, VTDP, and that resulted from the study by the late Roy Daka, Dr. Roy Daka, and Kurt Schinkel. They did a study as far as rates of displacement, vertical rates of displacement on benchmarks in the Northern Gulf region. So the VTDP developed from that, and basically there were projected rates of displacement for marks within the Northern Gulf region. And so we observed a number of those marks in these GPS surveys. So we would use those predicted rates of vertical change and validate it through GPS, and then come up with heights that we could constrain vertically for the overall network. The thing that changed as far as the 2016 is that we went back. We did not use the VTDP model on this one. They went back and they reprocessed the 2004, 6, and 2010 surveys to be consistent with the 16. And then they compared the differences, the changes in ellipsoid heights, to try to come up with rates of displacement, rates of change, and the velocities on these benchmarks. And so that took a while. And so all of that is done. It was, some of the rates some of the areas showed a little different from the VTDP. And so that kind of throws it in there where you have to do more investigation as far as to try to make sure that what you're coming up with is correct. And so that's part of what was different about this one. So we've got all that done, and we're close to the final publishing of these positions. They'll be loaded into the NGS database over the next couple of months, but also that 2016 information will be a part of because it's a blue booking project. It will be a part of the information that goes into the vertical transformation model. So this shows you a map of the marks that were a part of that 2016 survey. It looks very similar to a lot of the marks were ones that we've repeated in the prior 3 surveys. There's probably about 100 marks that were in those prior 3 surveys. In other words, they were the same as some of those. But we did, again, we tied in, I think there's 9 benchmarks in Mississippi, and those made connections to a leveling project that the Mississippi DOT, paid and had done. And basically, it was according to that Tech 50 study that Dr. Daka and Kurt Schinkel did. And so these were just ties, for the Louisiana network to that vertical network, those level lines, just to give us some additional information. So this information you won't see it on the priorities map, the GPS on benchmark web map, but because the information is blue booked and it'll be there, and this will be a part of that vertical transformation model. Now, we've gone through and looked at, as far as, excuse me, we've looked at, there are other marks out there that have not been observed since the 2006 survey. And so we went through and looked at those and have added those. They're not there yet, but they soon will be, as far as additional marks that have prior published orthometric heights that could be a part of the GPS on benchmark project. And so the purple, the magenta on this map shows you what is, the marks that are on that, the GPS on benchmark web map. So if you filter it for, just the state of Louisiana, it would show you those magenta marks. Well, soon we're going to add these other marks in. These are different from the 2016 surveys, but they're marks that have a history. And if you do GPS or OPIS share observations on these, well, then that will give us another observation in a time series, and it'll help in that vertical transformation model. Plus, it'll have those updated coordinates as far as going into the modernized NSRS, like Galen had spoke about earlier. So this is just showing you a screenshot of what it looks like as far as that web map and how, this information for any of those that get observed will just further densify the 2016 information that will be there and be a part of it. So that's everything I have as far as unless somebody has some questions.
Dennis, this is Tony. I've got one question. Hang on a second. Here we are. There was one request for the name of that photo editing software, and I didn't catch it quickly enough to be able to answer him directly.
Okay, it is called DS World, and it's really a program that it developed from. It stands for Data Sheet World, and it allows you to go in, pull marks, very similar to what you do with as far as when you do a mark retrieval on the NGS webpage. It has, similar options. You can do it by county, you can do it, by a radius, a list of PIDs, but it also has this, it's kind of geared also towards submitting photos and for marks. And so there's an editing function in there also.
All right, thank you. I'm going to wait a second, see if there's any other questions that come in. I don't see any yet. And since they've had a little time to put some in, I want to proceed by telling you thank you.
Okay.
For your presentation, and Galen and Kathleen. And I hope that the audience has been as well informed as I've been. And we look forward to another such event in the future. I'm going to see if any of the panel members have any last questions, and if not, it may be the end of the show.
Hey, Tony, is any of that history in writing?
What? Come down here, Cliff.
Is any of that history in writing?
What history? I'm sorry.
Everything you just said about all of the different surveys. And
Oh, Dennis, I have a question about the history of the surveys, particularly the ones in South Louisiana that NGS did and then went back and did some more. Is that in writing? Cliff Mounier asked that question.
As far as the I would have to check and see if there's been a compilation of talking about it. There are reports that are generated for, at the end of the project as far as what was done, for the processing and adjustment, but those would be individual reports. But that information should be available, yeah.
All right. Well, yeah, if you get a chance, please try to either get us pointers or get a compilation for us. That's very interesting.
Okay.
All right. Any other comments? Going once, going twice. I thank everyone for their participation, particularly Randy, who's been silent mostly in the background and twisting the knobs and making sure that all of this works. So thank you, Mighty Oz. Otherwise, thank you, everyone. That's the end of our show. We'll see you next time.
Thank you. Bye-bye.
Bye.